Let me ask you a question. What's the first thing you do when your phone won't turn on? Most of us will panic, right? We think, oh no, is it broken? Or did I lose everything? Now imagine a computer or a phone as a human being. The hardware is like the body, the bones, muscles, and organs. But without the software, the mind, the thoughts, the instructions, the body just lies there, lifeless. On the flip side, if you only have the mind but no body, you also can't do anything. That is why we say that hardware and software are the foundation of every information system. One provides the structure, the other provides the intelligence. And together, they power everything from your social media apps to massive business systems. So today, let's dive into how hardware and software work hand in hand to make the information systems possible. To start, we must understand what a computer system is and its purpose. A computer system is a cohesive collection of integrated hardware and software components. Its primary purpose is to meet user needs, from data processing to complex computations. It acts as a digital backbone of an organization designed to improve efficiency, decision making, and automate routine tasks. Now, let's go through its integrated components. Let's start with the physical foundation, the hardware. Hardware refers to the physical components of a computer system. Assembling an effective and efficient set of computer hardware devices requires an understanding of their role in supporting the underlying information systems and the needs of the organization. The computer hardware objectives are subordinate to but supportive of the information systems and the needs of the organization. When selecting computer hardware, you must consider the current and future needs of the information systems and the organization. Your choice of a hardware device should always allow for later improvements to meet the evolving organizational needs. Computer hardware has three main classifications: input devices, the gateway to digital interaction. It serves as the bridge between the user and the machine. Processing devices, the core, the one orchestrating the machine's computational power. And lastly, output devices, the interface to information, the one transforming information into something understandable for the user. In this section, let's apply the IPO framework. The computer hardware IPO processing looks like this. Data enters the computer via the input devices, CPU performs processing, and the results are presented through output devices. So, why does the distinction matter? First, troubleshooting. It makes it easier to diagnose if issues stem from physical failures or program errors. Then, optimization. It helps leverage hardware with efficient software for peak performance. And lastly, innovation. It drives new tech by aligning software with hardware advancements. Input devices are indispensable hardware components that establish the vital link between users, or the physical world, and the computer system. Their fundamental role involves capturing diverse forms of information ranging from human commands and actions to various real world data and meticulously translating this input into digital format. This conversion enables the computer to effectively process, interpret, and respond to the information received, forming the initial stage of any computational task. Let's go through the input devices for everyday interactions, starting with text entry, one example of which is a keyboard that converts keystrokes into characters and commands, serving as the primary text entry device. Next is navigation, an example of which is the mouse and the trackpad, which translates physical movements into the cursor, navigation, and selections, facilitating graphical user interface interaction. Another one is audio capture, which is represented here by a microphone. It captures sound waves and transforms them into digital audio signals for recording or voice commands. Then we have digitization. One application of this is a scanner, which digitizes physical documents, images, or objects into digital files for computer processing and storage. Now let's move on to more advanced data capture devices. First, direct interaction. We can see these with touch screens that enable direct interaction via touch gestures, common in smartphones, tablets, and interactive devices. Next, environmental data. We can see these in sensors that gather environmental data like temperature, motion, and light for specific analytical or control applications. And then biometric scanners, which is used to authenticate users by recognizing unique biological characteristics like fingerprints or facial patterns. Let's talk about processing devices, starting with the Central Processing Unit or the CPU, often called the brain of the computer. The CPU is the primary component for executing instructions and performing arithmetic and logical operations. It processes all program instructions and manages data flow central to any computational task from simple calculations to complex data analysis. It consists of three associated elements. First, the Arithmetic Logic Unit or ALU. It performs mathematical calculations and makes logical comparisons. Second, the Control Unit, which sequentially accesses program instructions, decodes them, and coordinates the flow of data in and out of the ALU, the registers, the primary and secondary storage, and various output devices. And third, the registers. These are high speed storage areas used to temporarily hold small units of program instructions and data immediately before, during, and after the execution by the CPU. Random access memory serves as the computer's short term volatile memory, providing high speed access for the CPU. It temporarily stores data and instructions the CPU is actively using for rapid retrieval. Information in RAM is lost when the computer is powered off, hence the need for secondary storage. The amount of data that companies store digitally is increasing dramatically over the years. And secondary storage, also called permanent storage, allows organization to store large amounts of data and instructions more permanently than main memory allows. Compared with main memory, secondary storage offers advantages of non volatility, greater capacity, and greater economy. The motherboard is the main printed circuit board or PCB acting as the central communication. It physically connects the CPU, the RAM, storage, and peripherals, allowing them to communicate. It provides the electrical pathways for data transfer, orchestrating hardware interaction. The efficient operation of any computer relies on the synergistic collaboration of these core devices. The CPU continuously fetches data from high speed RAM to execute instructions. The motherboard serves as the indispensable connective tissue, providing the foundational channels for this interplay and linking all other components. Understanding this integrated ecosystem is crucial for optimizing performance and innovating in computer architecture. Output devices translate processed digital data into formats understandable by humans. They are the final stage in the input process output cycle. Visual output. These devices present information graphically. Examples of which are monitors, which offer real time display for desktops, while projectors scale visuals for larger audiences. Audio output. So we have sound and voice. Speakers and headphones convert digital signals into sound. They are vital for multimedia communication and creating immersive experiences. Hard copy output. These are tangible records. Printers create physical copies of digital files, essential for permanent records. Modern devices often include multifunctionality like scanning and wireless connectivity. And beyond traditional output devices, we have haptic and actuators. Haptic feedback provides tactile sensations like vibrations, enhancing interaction. This can normally be seen in games as an enhancement to the virtual and augmented reality experience. The invisible foundation. How the system software orchestrates the computer's core. System software forms the critical intermediary layer between the computer's hardware and application software. Its primary role is to run the hardware, manage resources, and provide a stable platform for other software. It acts as the backbone, enabling the entire computer system to function cohesively by managing memory, processing tasks, and controlling peripherals. Now, let's talk about the master controller or the operating system. An operating system is the most vital system software, controlling all hardware and managing other software execution. Its key functions include resource management, task scheduling, input and output operations, and user interface. Examples of which are Windows, Mac OS, Linux, Android, and iOS. Let me introduce you to the computer's maintenance crew, or the utility software. These are programs that help perform maintenance or correct problems with the system. If the user is having issues with peripherals, hardware utilities can be used. For security issues, there's security utilities. For storing large files, there's file compression utilities. Spam filtering utilities to address spam messages the users receive. Now, let's meet the computer's translators or the device drivers. These specialized programs allow the operating system to communicate with specific hardware like printers or graphic cards. It acts as a translator, converting generic OS commands into specific instructions for the hardware. And without the correct driver, a hardware device cannot function properly. And lastly, the embedded brain or firmware. These are software permanently embedded into a device, read only memory, providing low level control for its basic functions. It provides the device's fundamental operating instructions, examples of which are the basic input and output system in a personal computer, software in routers, smart TVs, and digital cameras. In this section, we will talk more about application software. Unlike system software, which manages the computer's underlying operations, application software directly addresses user needs, enabling productivity, communication, creativity, and more. It transforms raw data into meaningful information through user friendly experiences. And here are some examples of application software. To boost efficiency, we have productivity suites. These are collections of applications bundled to enhance general user productivity. Word processing. This is used for creating and editing text documents. For example, MS Word and Google Documents. We have spreadsheets for organizing and analyzing numerical data. Excel and Google Sheets. For presentation, this is used in designing and delivering visual presentations. We have PowerPoint and Keynote. To connect with the world, we have web and communication, which plays an essential role for accessing information and interacting across networks. In this group, we have web browsers that enable navigation of websites, examples of which are Chrome, Firefox, and Edge. We have communication tools to facilitate interaction via email, messaging, and video calls. We also have a set for tailored expertise, and these are specialized applications and software designed for specific professional domains, addressing complex requirements beyond general purpose tools. Example of these include CAD for engineering, medical imaging for healthcare, financial modeling tools, and graphic design platforms. And lastly, we have on the go and connected softwares. These are mobile and cloud. Mobile applications are designed for smartphones, tablets, offering portable, touch optimized functionalities, while cloud services can be accessed over the internet, eliminating local installations, for example, Google Workspace and Salesforce. Beyond utility, application software can also serve as a catalyst for change. First, they provided democratization of access. Apps have made more complex tasks from photo editing to global communication accessible to a broader audience. It revolutionized industries from ERP systems to telemedicine. Application software continually redefines operational paradigms in every sector. And lastly, it drove digital transformation. The evolution of apps, especially with cloud and AI, is central to new business models and personalized experiences. There is a symbiotic relationship between system software and application software. System software provides the platform. It manages hardware resources and provides the environment for other programs to run, while application software performs the tasks. It performs specific functions for the end users, relying on system software to operate. Application software cannot run without system software, and system software exists to enable applications that serve user needs, forming a complete computational ecosystem. At the heart of every functional computer system lies a profoundly symbiotic relationship. This is not merely a collaboration, but a deep interdependence where each is essential for the other. Hardware provides the physical power, while software furnishes the instruction and intelligence that bring the hardware to life. Software provides precise instruction that hardware executes. This interaction is continuous and finely tuned for performance. Optimizing system performance requires a harmonious balance between hardware capabilities and software efficiency. To sum it up, hardware provides the essential computational power and physical framework required for any system operation, while software enables functionality, manages resources, and allows user interaction broadly categorized into system and application software. Neither hardware nor software can function meaningfully in isolation. They are deeply interdependent, forming a cohesive computer system where hardware provides the platform and software provides the intelligence driving all digital processes. That's all for now. Thank you for watching, and I'll see you on the next one.